So here we have attendees who, so we are having a conference here, TAROS 2024. So we have attendees here from member of public, and also we have attendees from the conference. So those who are attending, who are member of the public, so for them I'm just repeating what TAROS is, and then we'll move to the public lecture. So TAROS, this is 24th TAROS conference 2024, and this happens every year within different universities in the UK. So it started in 1997. First few years it was every 2 years, and then onwards it's every year. So yes, and this is the longest running UK hosted conference on robotics and autonomous system. And as a tradition of this conference, we host a public talk which is hosted by IET. So that's the public talk we are going to have now. So that's why we are here. So today we have Professor Asoke Nandi as our, so he will be giving the public lecture. So I will provide a very brief bio, and then his talk is about robots, past, present, and future. And so he will talk about his talk, so I'm not going to talk about his talk, but very briefly his biography. Is Professor Nandi received the PhD degree in physics from the University of Cambridge. He held academic positions in several universities, including Oxford, Imperial College London, Strathclyde, and Liverpool, as well as Finland Distinguished Professorship. So in 2013, he joined Brunel University London. In 1983, Professor Nandi co-discovered the three fundamental particles, providing the evidence for the unification of the electromagnetic and weak forces, for which the Nobel Prize for Physics in 1994 was awarded to two of his team leaders for their decisive contributions. I think that's a lot I said, so he has a lot of bio. I'm not going to read and bore you. So I would like to invite Professor Nandi for his public lecture. Professor Nandi.
Thank you. Thank you very much. I'd like to thank you all for coming, and also particularly if there are any of those who are not from Brunel, whether from public or outside in the conference. So a warm welcome to you from Brunel. This is, as was said, there is an IET public lecture. So I thank IET for having such lectures in the context of the conference. And also I like to thank the panel who chose me to give this lecture. So it's an opportunity. But I chose the topic to align with the topic of the conference. So you all know about robots, so you're all expert. But I'm not going to say so much about robots, but around it. But first, I want to start with something. The reason I chose the title is sometimes we come across something for the first time, and then we think, this has just happened. And robot is such a thing. Just in this case means that week or anything. But it's sort of a more recent things. But sometimes it happens that these things go back a long way. And in the case of robots, it does. And so I want to reflect and at least say a little bit about that. Because after all, there is a different set of humans who did think about such things and who did some such things. So we kind of acknowledge not individually them, but at least their work. So we are, as Newton said, we stand on the shoulders of giants. So that's why I chose this talk, the title. So these are the sort of the blue bits. So I'll say a little bit about brief history, and then I'll say something about machine learning, and I'll say more about that as I go along. And then closing remarks. What time shall I stop? 40 minutes. Okay. That will be hard. Okay. So, but before I go ahead with it, I just want to say for the brief history bit, I learned a lot from Wikipedia, so I hereby acknowledge that I have learned a lot from, okay, so thank you, Wikipedia. But I take responsibility for anything I say. So before I go, I want to tell you very briefly, just one slide about signal processing. Many of you may be familiar and some may not be. So signal processing is not something that people who don't do it not always realize what it is. So I want to tell you that because it's very, very central to everything that you're doing, and in fact everything that we do, meaning humans do, and more than humans, even nature. Life, I don't think, can exist without signal processing. I will explain myself. And so do robots. If we want robots, they have to do signal processing. So 3 domains are, I'm of course simplifying, so it's a general audience. So detection, estimation, prediction. Detection is like you can ask a question, the answer is binary. Is there anybody in this room? So it's not how many, just yes or no. That's it, binary. And so you're crossing a road and you'll be saying, is there a car coming? So that's binary, that's detection. And then estimation is you might want to know how far away the car is because you want to cross the road. If no car, you can cross the road. If there's a car coming, you might say, I'm going to wait. But sometimes a car coming and you still cross because you do 2 things. One, you estimate that the car is far enough away, and you also predict that you can cross the road before the car comes here. And those 3 are the basic problems of signal processing. But as I say, I simplified it. So you need all those 3 to live a life here. We don't get hungry and buy food always. We do shopping before. Many, many things. And even we grow crops. We decide on the season. And same thing happens for animals and plants. So life itself, without these 3 things, I don't believe the type of life that we know it can possibly exist without signal processing. So it's very, very fundamental to everything that lives. And so in brief history, they are not going to be exactly like that, but they're roughly sequential. But conceptualization, because when something old, then nobody actually made a robot, but people thought about it. It's like flying machines. Aeroplanes are roughly 100 years old, but people thought about flying objects millennia ago, more than a millennia ago. So of course they didn't have an airplane, I don't think so, but nonetheless it was in human conception. So same thing, robots have been in human conception, not with that name of course, but different way millennia ago. And initial robots, we had mechanical robots, and I'll take you through a little bit, not much. And of course electronic mechanical robots, and you can see a lot of these. I wasn't here earlier, but I saw some videos here, saw some robots outside. So Oxford English Dictionary, I looked up for this talk what a robot is, and it says a machine resembling a human being and able to replicate certain human movements and functions automatically. That's what OED says. And I also looked at, just to be balanced, Cambridge English Dictionary, and it says a machine that is controlled by a computer and does jobs automatically. But of course, I need to say these are a couple of modern statements or definitions, because they are not thousands of years old. They're only, recent. So, where are we? So, if we think about just the word robot, robot is a comparatively modern word. It has a Slavic root. Robot does something, meaning if it's robot something, the robot says basically is to do with labor. And you can see where it's coming from, it's labor saving thing, it's to do with labor. And the actual word robot was first used for a fictional humanoid in a 1920 Czech language play, and in English names is Rosam's Universal Robots. And the author was Carol Chapek. But Carol Chapek did not invent the word. It's his brother called Joseph Chapek. Joseph Chapek, he actually invented the word robot. So you can see that's about 100 years old, the word itself. But in terms of conceptualization, it's very much older. And that's where I'm going to say a couple of things. So, but the concept of robot goes a longer way than 100 years. For example, the idea of automata existed in mythologies of many countries, including ancient China, ancient Greece, and Ptolemaic Egypt. And throughout ancient civilizations, there have been many accounts of user-configurable automated devices resembling humans, but not always, and other animals, and designed primarily for entertainment. And more of that coming in the next slide. So now 11th century India, so 1,000 years ago, we are 21st century, so 1,000 years ago, there is this Sanskrit textile, the author is Bhoja, called Samarangana Sutradhara. It includes a chapter about the construction of mechanical contraptions, including mechanical bees and birds, fountains shaped like humans and animals, and the next bit, as well as male and female dolls that refilled oil lamps, danced, played instruments, and reenacted scenes from Hindu mythology. I'm not sure whether they existed or not. That's not the point I'm trying to make. But the point I'm trying to make is people at least thought of such things. So in terms of thinking, conceptualization, it goes a very, very, and that's 1,000 years ago. I'm going to tell you something else, which happens to be also, sorry, I had an arrow here, which happens to be also 11th century, but it's not talking about that. It's this Lokapananti is basically called kind of conventional wisdom type thing. It's a book. It's a story book. And it's actually referring to Buddha's relics, which is pre-Christ, which means more than 2,000 years ago. And it says that they were protected by mechanical robots. In bracket, of course it didn't say robots. This is the word, oops, sorry. I can't control, oh, there it is. Bhuta Bahana Janta. And they were discerned by somebody who definitely lived, because it's a historical king called King Asoke in India, and he himself actually died before Christ. So he's referring to things that are more than 2,000 years old. Again, I don't know if they're mechanical robots or not, I don't know that, but the point is referring to something. So at least in conceptualization, we had these things. Maybe not reality, I don't know. But of course, I jump a long way from not 1,000 years, but last century. In modern times, electronics, rather than mechanical, electronics became the driving thing for robots. Indeed, the first electronic autonomous robot was created in this country. Somebody called William Gray Walter in Bristol. And Professor Davis lives in Bristol. Maybe he knows more than I do about it. But in 1948, so that's comparatively recent, So 50 to now is 70-year-old. But that was somebody made one, but it's not a commercial thing. But if we go forward, the first commercial digital, that's interesting, digital and programmable robot is called Unimet. It was built by somebody called George Devil in 1954, that's 70 years ago. It was sold to General Motors, a company that you very well know, in 1961. And it was used to lift pieces of hot metal from die casting machines. So that was definitely a real robot, and the one in Bristol that I referred to. And this one actually somebody bought it, meaning a big company. Now, because General Motors car company, so coming forward, even now, I don't know if you know, but in car factories today, on average, there is more than one robot per human workers. So that's 10%. That's a significant number, you know. And this is not the real thing, of course, but it's a sketch of the Unimate that was sold to General Motors. And there's the arms, if you like, pick up the hot metal, and there's the base. But with the same name, but a different robot, was about 10 years after that. In 1967, you see here, this Unimate is pouring a coffee for a human in 1967. So, and this is getting what you might recognize as getting sophisticated and doing things. But of course, they don't have to be humanoid. You know, that's just one possibility, but it doesn't have to be. This is a humanoid looking. And Japan has been doing a lot of things in robots for a very long time. I mean, longer than, say, if you like, if you cancel the Bristol one I said. In modern times, Japan has been doing a lot in robots. And this one is called Asimo, and it was shown in Expo 2005. And, Expo 2, and I was in, I don't know if you know, there is an institute called Riken Institute in Tokyo, which is supposed to be their flagship place. You know, there are many different, not just robotics, but brain studies, chemistry, physics. This is their top place, and most of their, if not most, a great number of Japanese Nobel laureates actually work there. And my wife and I were there, I think 2010, I'm not quite sure about that. So it's not so long ago. And they had robots, we saw humanoid robots there, and there are a pair of them, they're actually dancing to music. But the reason I said pair is not just one dancing to music, there is some coordination between the two, you know, their movement. This one is again, modern times, because 12 years ago. This is a military robot. There used to be one called Big Dog. This is kind of, if you like, a newer version of Big Dog, but improved version. It's called Cheetah. And the reason I put that one up is you see here, Cheetah was clocked as the world's first eight-legged robot. And it's not just that, 28 miles per hour. You can't drive that speed in London. So the robot's doing better than we can do in our car in London. So that's kind of the brief history. But if you now kind of look now, you know, those are things. But robots are everywhere. Of course, they haven't taken over the world, and I don't think they're going to. That's not the point. The point is we are finding use for many types of robots, and of course developing many more new ones. And it's not that I'm not going to read everything. But you can see there are industrial robots, and they're not, by the way, everything either. But industrial robots, service robots, educational robots, they actually teach students, they're being employed in schools, you know, teach students. Military robots, like I showed you, Cheetah, that one. Of course, healthcare robots, there's a lot going on here. If you think of even the many surgery, they're surgical robots, and they need to go inside the body and things. And the mining robots are important because there are many types. Say nuclear reactor, you want to get some things. Now, no human going to go there because it's just too contagious, it's just too dangerous. But you can have robots which can go there, and generally dirty, dangerous, dull, or inaccessible tasks, then, well, you don't want to do it or can't do it, so you get a robot to do it. You know, that's the idea. And there are many, many others. So this list is not comprehensive, but this is just to tell you that it's actually just about everywhere, but it's very broad. So now I'm going to leave robots. And who I'm going to tell you about got, in some sense, nothing to do with robots. Who I'm going to tell you about machine learning, and big data, but mainly machine learning, but these are all using big data. And the reason I'm going to do this is I want to show you, and you probably already know, but in case you don't, I want to show you it's not that machine learning, it's not that they are better than humans. I'm not saying that in a general sense. But there's specific task where these things can do far better job than any human can and ever will. And I want to, that's not to say they're better. I'm saying for specific that we can do many things. These things can't do many things. They're very restricted in what they can do. But the point that I want to make is that things that they can do, they can be made to do very, very well beyond any human ever will do, or certainly does now. And that then I'll try and bring the two together. And so first I'm going to tell you about communication. Before I do, machine learning, of course, they are, you all know about machine learning, but I'm saying here there are an alternative way of looking at machine learning, and an alternative kind of description would be is kind of developing tools for discovering structures. By structures, I don't mean physical structures. I mean data structure, look things within the data that we might not spot. So, and also discovering rules. They can, in principle, look at a game, like say you're playing, it doesn't have to be chess, but like you're playing, doing something, and they can discover rules for it. So even things like there are things where you come in, say you come to the office, and first thing you come in and hang your jacket, and you might go and get a cup of coffee or something, or there may be a fridge in the corner somewhere, and you do that. And after a while it will know that that's what you're doing, and that's kind of, it learns. So by watching, so one doesn't have to tell what somebody is doing, but just watching, it can develop some of these things. So discovering rules, and of course the main thing that the world is waiting for or doing is application. They think they got something good and they want to do everything with machine learning. So that's the application. So I want to tell you about communications and those who are initiated the many types of learning. So machine learning, but there are many types. We name them. There's supervised learning, there is unsupervised learning, and many, many other. I'm not going to go through. But I'm just going to take two, supervised learning and unsupervised learning, and I'll give you some examples in this specific case. So this is a classification problem. And what is the problem? Exact problem is that these names, if they don't mean anything to you, don't worry, you don't need to know. But let's say that this is a language, it's only got 4 alphabets. English got 26 alphabets. But this language here got 4 alphabets, A, B, C, D, that's it. And then this is another language, and this language got 16 alphabets. And this language, yet another third language, and this has got 64 alphabets. That's it. So what's the job? What's the problem? The problem is, you look at this, and you have to say, is it a 4 alphabet language, 16 alphabet language, 64 alphabet language? Now you might think I'm a fool asking you the question, but that is the problem. And anybody who is not blind, anybody of the 8 billion people in the world who is not blind will be able to say this, absolute accuracy, whether it is 4, 16 or 64. And this we designed, this is sort of my group's work some time ago. This is 30 years ago, so that tells you how long I've been working in these things. A machine learning algorithm can find 100% accuracy. Now that's nothing great because everybody can do it, so that's nothing. But in this bracket it says noise free. I mean the signal that you're receiving. Sorry, this is communication, so it's to do with signals. Signal that you're receiving, they're noise free, i.e. they're very clean signal. Now, of course, it's easy, but real life is nothing like that. There's always errors or dispersion and many other things. So this noise free state, basically means if a signal to noise ratio is infinite, basically there is no noise and whatever you have is signal. But I'm going to add some noise to it. So this is the same thing, except now it's not it's not noise free anymore. I've added some noise, and if that doesn't mean anything, doesn't matter, it's noisy basically, take that. And what you see, you look at this, and these four are still separate, although they have got bigger. They're not point source anymore, if you think about that way. But they have got bigger, but you can still, everybody can tell that's four. Here, well, there is some overlaps, but given the choice 4, 16 or 64, everybody will say that's 16. Not 4, not 64, it's 16. When you come here, nobody's going to say 64. You don't know what it is. It could be just noise and nothing else. But this is where the power comes in. Look, the same algorithm that said 100% that everybody in the world can do it. This one is 100% accurate here, is 98% accurate here. Here is 98% accurate. And I challenge any human to do it. Nobody's going to do it. So, as I said, it doesn't mean machine learning cleverer than us. It does mean they have the ability to do some things better than us. And this is one thing. So I'm going to add a bit more noise, I think. I don't know if that slide here. Yeah. So now it's even more noise than the previous slide. And this is still, everybody would say that's 4. No clue, 16 or 64 or anything to do with the language. No clue here either. But the same algorithm, the very same, I'm not changing algorithm between slides. It's the same algorithm. It tells you 95% accuracy, that's 16. And that tells you 95% accuracy is 64. So this is incredible, the power of these things. And in fact, IET, it's his modern name. It used to be IEE. They gave me a prize in 1998 for this work. So I'm going to move on to something else now. Oh, this is written in a book, but I'll move on. And now I'm still using supervised learning, if that means anything to you. If it doesn't, don't worry. And I'm going to give you another example of that. And here, again, I tend to do research on different areas and write a book. So that's the book about condition monitoring. And here the problem is that there are some bearings here. This is the bearings. And, anything rotating like a car, the engine, or washing machine, or dishwasher, when they work, because you hear noise. And the good thing meaning in terms of doing science or engineering about these things, is you don't have to actually excite the system to get the noise. You just switch it on, and it will tell you why. And if it's not feeling very well, noise will be different. It's like a child, When they're crying, you know that from when they're laughing. So same thing here, not quite, but similar. And so the idea is from the vibration to detect if a thing is working well or not. And so I'm going to show you some data. That's not our data. It's from CWRU, and that's the Case Western Reserve University. So it's a university in the United States of America. And so it's their data, and it's publicly available for anybody. And there are some numbers, so I'm not going to go in detail in here. But what I want to tell you is there are these different methods, and in these methods there is a part called CS, that's called compressed sensing. Now, right, so the world, the world that you see here is an analog world. But the world that's in here, even the photographs of people you have taken, they're actually digital. So when we capture things or store things in a computer and many things like that, we convert the analog world into a digital world. And to do that conversion, we use something called sampling. We have to sample the signal. And you can't sample the signal as you like, because if you don't do it right, it's not right meaning you must do this, but it's a range. The sampling frequency must have a certain characteristics, otherwise you're going to mess up the signal. And that is worked out roughly 100 years ago by somebody called Nyquist, and there's a Nyquist theorem. And that's tell you that the minimum frequency of sampling must be above a certain frequency, tell you that. And what it is, you don't need to know, but I mean, for now, for the lecture, but there is such a thing. And that theorem is correct, it's not wrong. But I'm going to tell you that sometimes you can break that theorem. So Nyquist theorem is still correct, but Nyquist theorem was done for all signals that there is and there can be, meaning even the signals that doesn't exist. It will be true in 1,000 years' time and 1,000,000,000,000 years' time if you're still around here. So, but what's new, this is the signal processing bit, is that we discovered about 20 years ago it's possible to break the Nyquist theorem and sample a lot less. And I'll come to why in a minute. Lot less, and signal will be perfect for a certain class of signals. So it's not all classes of signal, certain class of signals. And what's more is that this class of signal is not just 10 signals in there or something. It is the membership of that class is infinite. So it's a huge class, but not all signals. But there are infinitely many signals in there. And this is kind of an area that where I thought might work. So this is our work that we did. I told my student that let's work on this. And so these numbers here are basically that. If it's 1, sampling rate is 1, it's normalized. 1, that means it's Nyquist rate. And if it's less than 1, that means we are violating Nyquist every time. But look at the testing accuracy of the condition of the bearing. And these are real data, not generated data. And you're getting 90%, 80%, almost 100%. And so you're still doing very, very well, incredibly well. It's kind of unbelievably well, but that's how you're doing. But to do this, there are 2 contributions here. One is the CS bit, which is the latest discovery, if you like, realization in signal processing 20 years ago. So that's the signal processing, and this is the bit that machine learning. Of course, it's a special type, but nonetheless. So this is what he created. And you can see you can take 1/10 of the data that Nyquist want you to take. So it's only 1/10. And you can still get roughly 99% accuracy. So that's incredibly powerful. And so what's happening is understood. But what I want to tell you is if you think about these things, there's a lot of data going on. You're always communicating. Particularly with images. Speaking is not a problem. We don't use that for speaking anymore. We look things up. And photographs and send photographs to people and this kind of stuff. So that's why, and they're very busy. And for that kind of thing, you could actually use a lot less data. And if you use a lot less data, your battery usage would be a lot less. And also your communication costs, sending the data, would be a lot less. So if you're thinking of green environment, then it would be better if we get rid of this in some sense, but I'll be a heretic, won't I, if I say that in public. So, but failing that, if we can use this type of ideas to be able to do that, because we will save the environment. Not completely, but we'll help it by a long way. Okay, so again, you can see that it's immensely powerful, these things. It doesn't mean they can solve every problem, by the way, don't get me wrong. I'm not here to tell you it will solve every problem. That's not going to happen. But when it can be extremely powerful. So, and not only it gives that kind of accuracy that you saw and how long it takes, for this kind of data, it takes here, when you use all the data, 6,000, you get 65 seconds it takes. and with 600 you get 7 seconds. So it's actually quicker, so a lot less computation. Okay, now I give you an example of unsupervised learning. And in machine learning, there is a thing called clustering. Clustering is, I can ask a question here, you know, how many sort of females in the room and how many males in the room. And that's clustering in the sense that I've taken an axis, male and female, so that's 2 clusters. Or I could say how many people with glasses and how many people not glasses. That's again along the line of glasses, you know, it's 2 clusters. So that basically clustering is grouping objects or people together along some properties, and it could be multiple properties, by the way, but along some properties, and that's clustering. And I'm going to talk about brain. I'll miss all of these because I don't have time. So I'll just say 1 or 2 things about this. This is when I was a Finland Distinguished Professor, so I was working on this kind of things, and this is based on 29 healthy subjects, and roughly female and male same number. Well, there can't be same number because 29, but as near as same. And what's happened is that the people is an MRI scanner, so they lie flat on a bed, you know, a trolley or bed, whatever you like to call it, and then they go under the strong magnet, and their brain is being scanned. But not just the brain, or it is brain, but it's called functional MRI. In this case, functional bit is they're listening to music, and we decide what music they should listen. So all these 29 people, they all listen to the same music, and while they're listening the music, we actually record what's going on in their brain. With the MRI is like, you know, CT scan in a manner of speaking, meaning you can create a 3-dimensional representation of something, and that's exactly what it does. So it logically, the brain is horizontal slices. It logically slices the brain, many slices, and at any one time is looking at a 2-dimensional object, a slice, and then it puts it all together back into a 3D volume. And what I'm going to show you in a minute, it's a video, is a brain. Of course, it's a representation of a brain, but it's not a single person. It's the average of all the 29 people there. So it's an average brain of these 29. And and you'll also hear some music. And the music is exactly what these people heard. And it's all synchronized. And the other thing is, on the representation of the brain, you will see 2 colors. So we are trying to look which bit of the brain responds to the stimuli, which is the music. And so, of course, it's a continuous variable, if you like. So to make things simpler, because for the uninitiated, I just choose 2 colors. So when it's red, it means it's strong response. And when it's blue, meaning kind of no response, very little, you know, it's not doing anything. And if it's red, that means it's really busy, that particular bit of the brain. And so that's what we're going to see. And I'll show you, because I can't talk because there will be music soon. And so because it's logical brain, we can, you know, if you look at if you had image, normal image, like CT scan, you can only see from outside. You know, it's like my head. You can see what's everything, but you don't know what's inside. It's a logical brain, so we can actually cut open and open up because it's logical, so we can do that. And it will be done, and at that point I'll stop. So, I need help. Oh, keyboard. Oh, yes, started. The best way to watch it, I think, fix on one area of the brain that you choose, and and see its color change as the music changes. So this is blue, and you see it's still blue, but it's changing. And this one is red, and still red, but it's changing. So this is all on the surface, but hopefully soon it will open up in the middle. So this is the frontal lobe, so this is here, and this bit is the back of the head. See inside what's happening. Okay, so let me see. Oh, so what this shows that I think, I don't know, this is I think one day possibly we'll hear music without our ears. Why do I say that? I say that because brain works on electricity. It's the exchange of ions, in the cell. So brain works on electricity, and already not for this, but for other reasons, we do in hospitals, we meaning not people like us, but hospital, doctors activate the brain they give electric shock for different reasons, and I can explain, but that happens. So I think, so why do I say we might be able to? So at the moment what happens, we hear, and there are lots of little sensors in the ears, and they produce electric impulses, they go through, and then they end up in the brain, and that's why you're seeing red and blue. But supposing we don't have the ears, maybe we figure out this piece of music equal to this pattern of red and blue. And then we program the red and blue using electricity. Forget the ears. Now, may not be in my lifetime, but it just may happen one day. So now, so why did I show machine learning for? I think because, we talked about our forefathers or foremothers, they thought about robots or automata, and they wrote about them, they conceived them, and of course, 100 years ago, we had sort of robot word, and then we had robots, and now we have more complicated robots, and so on. And it will go on. But the brain, for robot, for something that exists physical, then you need a body. Whatever shape the body, doesn't matter, whether humanoid or not, doesn't matter, you need a body. And the body will come from, many, many things. There are new materials, thinking about the future. That doesn't mean they'll all be used. There's 3D printing. And there are many other developments that's to come. And I'm sure that's the body, where the body is going to come from. If I think about brain, I'm confident that for a very long time, that brain will be machine learning. That's how it's going to work. And then, so I'm more sure of that. But where I want to also take you, where the young people in the room or around the world need to think about is that these robots or even machine learning algorithms or whatever we can make from them, make out of them, is to think about this. In our society, or humans, thinking about humans, we do a lot of course we argue and we fight, but having said that, but we also work together a lot, whatever form or whatever way, i.e. cooperation. And this cooperation, and there is a bit of it happening in robots, but I think that's an area of research. And it's not research meaning building it, because a lot of these things is to think about how they can be done rather than just doing it. So it's not, first step is not doing it, but it's to think about it. And I think there is a lot for us to think about cooperation to be introduced much more in robot world. If you might want to change a bulb in your house, and you might have to get up on something, or even a ladder, you want to get to the roof, somebody might hold the ladder for you. And robots, they don't do that at the moment. So we need that, not exactly that, but that kind of thing. The other thing, the robots, the motivation, they don't really have motivation. So we have to have a way of finding how to give motivation, how to make it generally. You don't give it motivation by itself means that they generate themselves. But what I mean, we need to think about how to introduce them into the robot world. And that's not easy, but then we're not here to do easy things. We are here to think about hard things and make it happen. So that's something to dream about. And kind of very related, but curiosity. Curiosity is not exactly, I don't think they're the same thing, curiosity and motivation. There is a difference. And one difference is that, if you sit and see something, if you meaning a human, something they don't know or they haven't come across, but once they see, they get curious about it, and they try to make something out of it. And this kind of thing, so what's happening, I think the kind of rationale for that is that, in evolution we have been, we are very sensitive to movement. If you are, sorry, I'm going away, but I want to come back, but I want to explain something, or at least say something. If you're in a room and you're very concentrating and you're doing something, and if something moves in the room, like somebody came in, they don't have to make a noise, but you actually know something's happened. And the reason is that evolution, motion is very important, because it might be an enemy. Or, I'm not saying you're thinking the same, but we are all, we meaning not just us, cats and dogs and everything else, they are all queued up, they're clued up to notice movement. Not only that is, if you lose something small on a floor and you can't find it, so what you do, and people do that, everybody does that naturally, I've seen it. So what you do, you don't look like this if you can't see it, you move your head. The thing is not moving, but your head is moving, so it creates emotion, and you see it easily. And similarly, if the thing moves and you're stationary, you can again see it easily. So there are a number of things that you get curious about. And I think this curiosity is something that we need to see or think about how to introduce into the robot world, so that we don't have to tell it to do something. Sometime you come home and it thinks you're tired, and then it makes you a cup of tea or something. So automatically, without asking for it. So you don't have to press the switch to get the light on. And, sorry, one more slide. So I would say, I like to say we are in a very special and exciting period. And I don't say it because I don't say it just because I'm here standing in front of you. But I do think, confluence of machine learning, electronic engineering, mechanical engineering, I'm not just choosing those names, but the kind of things they do, and signal processing can create opportunities of quality that have not been possible before. And it's simply because of many, many developments, and it's not just we have done it in the last 20 years, but it's a human history. And I also think that 21st century robots will be driven by machine learning and other developments that's to come yet. And they will definitely change the way we live. That's not to say they will take our jobs or something, or they're going to take over the world. That's not the point. But the way we live is going to change. That's for certain. And I just hope that these will be a force for good for the world. You know, with any of these things, like machine learning, you know, you can do a lot of bad things. And people, particularly AI, doing a lot of bad things at the moment. And they always have done. I just hope these things will be a force for the good for us and the world and everybody else, animals as well. Thank you.
Thank you very much for your very, very interesting talk. We have time for a few questions. Yes, of course.
Thank you. Thank you very much for the fantastic talk, Professor Nandi. I hope you don't mind me to add something to your talk. You mentioned already the fantastic tradition that we have in the UK in robotics. You mentioned William Gray Walter and the robots he developed in 1948. So I can add that 60 years ago, Professor Meredith Thring came to Queen Mary University of London and started their robotics activities. So it's exactly 60 years now. And I want everyone to look up Professor Meredith Thring at Queen Mary University of London. Fantastic work already 60 years ago.
Thank you.
Thank you. Any other question? Yes. So it's a bit far. It's all right.
Thank you very much for the talk. It was actually very interesting. Considering the body and the brain of the robot independently, like two systems that interconnect with each other to create the robot, wherever that is. In your view, what is more advanced right now?
What is
more advanced, the brain or the body at this point?
I may be biased, but you have to ask all the other. I think the advanced. Well, so it's a very good question actually. But before I answer the question, I can say one or the other, but I want to give some rationale. So, body is important, and my answer is the brain, but that's not fair completely, because I need to explain, and this is what I'm doing. Body is important because, by given a certain type, like humans, I can do this, I can't do that. It doesn't go back. But I can probably make a robot that can go every which way. Do you know what I mean? So body limits how much our dexterity, how much I can do. Also, I got fingers, so I can actually do, and there are loads of nerves here, as you know. So there are many things I can do with this in terms of feeling and even doing something, not just feeling in the sense of sensing, in terms of doing something. But many robots can't do that because they're not that sophisticated enough, So body is extremely important because it limits how much they can do. So what is advanced now, I would say it's very difficult, but I would say, let's think of the future. I think we need to develop both, meaning the brain has to be developed, that's through machine learning, my feeling, that's what's going to happen. But I think we need to think about the mechanics, if you like, of the body, whether it's humanoid or not, that's not important, I think, is that. And also, sometimes we all do it, everybody, to different extent, but we are kind of caged in ourselves. We see things and we think this is the only way the world is. But yeah, maybe the world is like that, but maybe there could be a better world if we thought differently. And now with these kind of construction, we are kind of fruits of evolution, if you like. But these are not fruits of evolution in a different way, that we make them. So we can make them how we like. They don't have to stand on 2 feet. They could stand on 4 feet if that's better. So I think we need to be quite open-minded. We don't have to have humanoid robots.
Okay, thank you very much.
Any further question? Okay, so I'll come later on that direction.
Thank you very much for a fantastic talk. You've discussed kind of robots and humans kind of cooperating together. How about combining them more physically? So I don't know if you remember the work of Kevin Warwick many years ago, where he had implants put in and things. Have you any thoughts in that area?
Well, sort of, yes. And in fact, Kevin, I know him. I think it's public, but I can tell him. He said he developed this thing, one of these things where he knew, his wife had the same. So they could track each other. They knew where they are, what they're doing, roughly speaking, and so on. Now, it's not, I think it depends to what you go. I mean, it's not that, I'm not saying it's bad or it shouldn't be done, but a lot of the robots that we're thinking about in terms of application is kind of doing things for us in some ways. So we are being selfish, I have to say, but that's what we're doing. And so in that sense, I think cooperation is fine, because that could be quite positive. But we don't have to feel we're the same, or I don't know, we have to play with them, and not that we shouldn't play with them, or we have to have dinner with them or anything like that. But cooperation is important. I think that's a very good question. I often think that may be a good way to learn, actually, because I'm not very good any games that I play, but I play many different games, and I find I like playing with players, whatever game that may be, who are better than me. And the reason, of course, I get beaten, but that's the bad thing. The other thing is that's for me, that's much more interesting, because it's making me strive to do that. And in that sense, I think that cooperation would be good. Yeah.
Okay, great, thanks.
Thank you. Thank you. Yes, so before we have Federico.
Thanks, Ralph, for the presentation. Of course, the technology is incredibly exciting. There are also dimensions of regulation, though, emotion, trust. There's a lot of research going on there, human-computer interaction and other disciplines as well. So what do you think is the way forward?
Yes. I knew this question was going to come up. I didn't know who from, but yeah, so I think that's a very good question. And I think, our meaning, in this room, and I hope I don't misrepresent, we are always thinking of the science, of the engineering, kind of make things happen. But that's not all, that's not the full story. If you think about, I'm not into politics, in this room at least anyway, but I'm not into politics. But if you think about, making hydrogen bomb or atom bomb is a great human feat, but dropping it was inhuman. So what I'm trying to say is that people who made it happen, they are scientists, and they were more motivated by, well, they're of course hired, but given that they were hired, they're more motivated by making it work. Nobody knew exactly how it's going to work, and there are many uncertainties, but they made it work. So in a way, we're trying to do that kind of thing. I don't mean atom bomb or H bomb, but making something work. However, when it comes to then use it, I think wider public has to be involved. We all in this room have to be answerable to the public, because we are part of the public, anything that affects them, or anything that could possibly affect them. So I think regulation is very important, and society should decide that sort of thing. We are, of course, part of the society, but we shouldn't be standing up saying, oh, yes, these don't have to worry about it. Well, we must say it, but they don't have to buy it. They have to do regulation. And the other thing that's happening in the world, and it doesn't matter where you are in the world, that the technology is, if you look at lawmaking, doesn't matter which country, well, I don't know, Russia or something, but generally speaking, if you look at countries, it takes a long time to make a law. And when I say long time, I don't mean week, I don't mean a month, and I don't mean 6 months. It takes a very long time. And technology over the last 20 years particularly, or 30 years, they move much faster than that. So by the time lawmakers make a law, they made a law on something that's gone. So the world government, doesn't matter where they are, they have to think how to regulate these things and how to make laws quickly enough around that. And public must be involved. So it shouldn't depend on us, meaning who makes this stuff. It shouldn't depend on companies who makes and sells it. It should depend on the public through their government. There should be regulation, both for not just robots, AI as well. Yeah.
Okay, thank you for the talk. I want to ask, add on to the previous question, would you consider prosthetics robotics or would you not? And what do you think about its advancement?
Well, the thing is okay, I'll give you an answer. I don't know which side of the fence you are, but you know, sometimes these, if I knew why you are asking, I might have been better saying something much more sensible to your question. But I'll give you one example. I'm kind of, you know, backing away from your question. You know, before meaning, say, I don't know, 60, but certainly say 100 years ago, you had Department of Mechanical Engineering and Department of Electrical Engineering, and they are completely separate. And now, in this room, I bet there are mechanical engineers, computer scientists, electrical engineers, and many things they need. You got robotics. Is it mechanical? Is it electrical? Is it computer science? I mean, or you look at something like prosthetics. You know, there are many, many things where there are a lot of biomedical engineering, which is both in mechanical and electrical. So I'm not quite sure is it helpful to look at it like that. But coming back to specific question, I would say it's more kind of not robotic prosthetics. You know, because prosthetic could be something that's very different. Yeah, it's not. But of course, there are always things you can come where things are actually, you know, connected up.
We may have time for one more question, if there. Okay.
Thank you so much for this valuable presentation. Is it possible to put in a few words to distinguish between machine learning and artificial intelligence?
Machine learning and?
Artificial intelligence.
Artificial intelligence.
The AI.
AI is, in some senses, broader than machine learning. I mean, for a start, you know, you can look up, and many people probably will have different views on it. But machine learning is almost like, it's simplified, but I'm just trying to say, it's getting a machine to learn something. Right? So, in a way, but artificial intelligence is broader, meaning I would say it obviously includes machine learning, but there are many other bits to it. That's not quite machine learning. And artificial intelligence, at the moment, is if you think about work like in the old days, in Brunel, that's long before my time, the two very famous professors, and I can't remember their name, but they have gone. They left us some time ago. But there was a department of cybernetics, and they were very, very well respected, maybe you know, world famous professors. I think F.A. George was one of them, and there was another one. And they were doing cybernetics, which was kind of more than machine learning that we do it now. He was thinking, but of course, you might say, well, it wasn't so focused then. You know, we're talking about maybe 60 years ago or something. So you might say, well, you know, things weren't so focused, so what they're doing. But if you look at what they're doing, so it was broader than what we call machine learning now. Yeah. So character recognition and many other things, you know, face recognition, you know, they are all machine learning. But artificial intelligence is a lot broader than that. But I think some of these things, you know, it's my pet thing, is when somebody or even a group says, oh, this is robots, they haven't thought much about it. And when I say, I don't mean in a bad sense. What I mean, we can only think at any one time within the context that we do think. And then when there are new contexts, we have to look at these things. We don't go backwards because we have a word that we created and then we stay with that word until somebody bring a new word. So my advice is for working engineers and scientists, words are important, but don't get too much into semantics. Yeah, because it's not helpful to move the subject. Yeah.
Thank you very much for joining us today. So I hope I will see most of you tomorrow as well. And thank you those people who, from member of public who joined us for this fantastic talk. So hopefully we'll invite you to our next public talk. Thank you, and see you in the morning.
Thank you very much.